So this is an update version of the presentation is there. The talk will be about work we have carried out recently to develop systems that are able to predict the accuracy of their decisions. In the long term, we hope these developments will help making artificial intelligence systems that are more aware of their knowledge limitation, and I will elaborate about that in a minute. The talk will be fairly technical, but before going into the technical discussions, let me let me outline what the great wise men of antiquity said about knowledge and intelligence. First, of course, we have the famous saying of Socrates, I only know I know nothing, and similar saying by Confucius and others, and also the more elaborate one by Aristotle, the more you know you don't know, which is deep thinking. This kind of thinking is nowadays considered intellectual humility, and similar reflections are attributed to many other great thinkers like Da Vinci, Descartes, Newton, etc. In contrast, if you ask nowadays artificial intelligence agents, what you get is this kind of arrogant responses, which essentially say they know everything and they have no limitations. And what I think is it is actually this lack of intellectual humility of these systems which leads to the so-called hallucinations and other negative results that these systems usually provide. So the conclusion is that we should struggle to make artificial intelligence systems not only intelligent, but also, and more importantly, wise. The talk will go around the statistical decision theory, which the statistical decision theory is one of the basic pillars of pattern recognition and machine learning, which in turn are currently are the driving forces of modern artificial intelligence. However, in nowadays work on artificial intelligence, you very seldom or ever find mentions to a decision theory, which is a pity because decision theory principles, concepts, and implications are simple and easy to understand, and understanding them allows to properly deal with interesting tasks such as error or accuracy prediction, which is the focus of the talk. The talk will be technical, so I will need a bit of notation. X will be used to denote data or observations from some domain, and each observation is assumed to belong to one or more classes. The classes are denoted as integers from 1 to C, and note that the concept of class will be used here only in a metaphoric way, because most of what I am going to say directly applies to more complex tasks such as machine translation or video understanding, where the number of classes would be huge or maybe infinite. The relation between observation and classes will be statistically modeled by the joint distributions of observation and classes, which is denoted in the usual way in statistics. And from this joint distribution, it is straightforward to derive the unconditional density of observations here and the class conditional posteriors for all the classes. Going now directly into the decision theory, perhaps the most important result is the so-called optimal base expected error, for which we need to assume that the joint distribution of observation and classes is known. I mean the true one, the one that happens in nature, but we don't know, of course. And of course, we also know the unconditional density and the class posteriors. And if we have all this information, then it is easy to show that the best decision you can make for each observation is to decide for the class for which the posterior probability is maximum. And if you make this decision for every observation in the domain, then you get the so-called optimal base or expected error, which is given by this formula, which depends on the unconditional density and the class posteriors applied to the optimal decisions. This is very, very theoretical. It's far apart from our objective, but we can, because in practice, what we will have, we will not have these probabilities, but we will have a classifier which is trained from training data, and this is related with the posterior probability that can be trained from the training data. So, let's consider that a trained classifier, which is trained for a given set of training data, finite set, and from this set we can estimate the posterior probabilities and then have a different decision rule, which is similar to the previous one, except that now the P has a hat, which means that it has been estimated from data and is not the real or true posterior probability. Plugging this decision into the expected error, then we get the expected error of the trained classifier, which is essentially the same, except for the class that is used for the integral, which in this case is the class predicted by the trained classifier. This is a bit closer to our goal, but again, in order to compute this expected error, we need the true probabilities, the two distributions, which are unknown. But this equation suggests a naive approach, which is to replace the unknown distributions by distributions that you can train for the given training set. In particular, we already have the capital P hat, the posteriors, so we assume that have been trained from the training set, and we can also train a class, an unconditional density from the same training data. And this leads to what we call the naive base expected error, which has the same form as the previous equations, except that here everything wears a hat, which means that everything can be computed once you have the models trained from the training data. You don't need any other thing. While it is easy to show that the trained classified expected error will be always higher than the base error, which makes the base error a lower bound of the error probability that you can get with any classifier, we don't have a similar result for the naive base expected error. But the intuition says that this will tend to be significantly lower than the base error and also, of course, lower than the trained classified error. But our hope is that there will be functional relationships between the trained classified expected error and the naive base expected error, so that we can discover this function or this relation in order to calibrate this quantity that can be computed without class labels and so on, and in this way estimate the real error. Well, this is not the end of the story because all these errors are expected errors over the whole domain. And in practice, we will never be interested in knowing what is the error of a classifier over the potential infinite domain, but we'll be more interested in knowing how our classifier behaves on a given test set. And so we need discrete versions of this equation in particular, and also of this one. So the discrete versions are here. This is for the naive-Bayes expected error applied to a finite test set, S, for which we don't need class labels. And this is what we call the empirical error, which is computed for the same test set, but in this case using the correct or real class labels, which are assumed to be available in a given test set. So our aim is how to convert, well, to compute this, which we already know how to compute it without using the class labels, and then to convert this into this as exactly as possible. So this is done by calibration, and we propose to use a power function, calibration function, which has two parameters and is flexible enough to accommodate different tendencies. For instance, if beta is 1, then it is linear with a slope alpha, or if beta is greater or lower than 1, then it accommodates convex or concave tendencies. So we hope this will be flexible enough to accommodate all the possible relations between expected error or estimated error and empirical error. Well, this is not enough yet, because in order to estimate the parameters of this function, what we need are pairs of values of the estimated error and the empirical error. And then if we have a test set or a calibration set in order to estimate these parameters, this calibration set needs to be divided into a number of disjoint groups so that we compute the estimated error and the empirical error for each group, and so we can use these points to estimate the parameters of the calibration function by mean square error regression on the points that we have obtained. It is interesting, well, I should say that the groups can be natural parts of the ground truths available. I will show an example later. Or if there is no natural division into groups, then they can be artificially built by sorting the data points by increasing order of their base naive error, and then grouping the points sequentially so that the first points will have low error and the final points will have, the final group will have a higher error. In any case, it is important that the sample of the groups exhibit different degrees of difficulty and therefore different values of the estimated and empirical errors. Well, once we have the calibration function, it can be applied in order to estimate or to predict the error of any given test set. S will be a test set. And the best approach we have found is to divide the test set also in groups, as in the calibration set, and then calibrate the estimated error of each group, and then average the calibrated results. This is all what is needed to predict the error of a classifier, but in our experiments we will be interested to know how close this prediction is to the real or predicted error. And for that, we will need class labels in order to compute the predicted, the empirical error. Once we have the empirical error, then we can just compute the discrepancy between them And then we normalize it by the empirical error in order to have a relative error which can be compared across the data sets and methods. Well, let's talk about application. First, we have applied these ideas to many benchmark classification tasks, large tasks, and then we have applied to a more complex task involving sequential decoding, which will be handwriting recognition. Let's go to the conventional classification task. We have considered many tasks, but here I present only these 7. 2 of them are about classification of text, for which the classifier used is Roberta. Then we have 4 tasks of image classification, for which the classifier are variations of the ResNet classifier or the convolutional network adapted to the specific task, and also a task of classifying electrocardiogram signals, for which the classifier is the so-called multimodal information function, followed by AlexNet. In any case, all the classifiers have a finite layer, softmax finite layer, so that we can get estimates of the posterior probability, which is what is needed to estimate the error. And here is the results we obtain. This is the empirical error, and this is the predicted error. As you can see, the discrepancy is very low. The relative values of the discrepancy are below 5% for most of the tasks, except for the tasks which have a very low empirical error, which, of course, because the empirical error is in the denominator, it is more difficult to get a low relative error. In any case, it is clear that this accuracy of the prediction is more than enough for many possible applications of this technology, including the development of artificial intelligence systems that are aware of their knowledge limitations. These are the calibration functions, the first row, for some of the tasks. And these are the test set or the evaluation set data plotted along with the same calibration function, so that you can see that the tendency represented by the calibration function carries over very well on the evaluation set, and this is why the results are so good. Well, times fly, but I don't want to finish the talk without saying something about the complex task of handwriting recognition. So I ask you a bit of patience, so maybe 5 minutes to finish the talk and talk a bit about that. In fact, this task was the driving force to start these developments, because in handwriting recognition, you typically train a system and so on with a few hundreds or maybe a few thousand page images, and then you apply the models to huge collections of maybe millions of images. And so it is impossible to predict, it's impossible to compute the error rate that is expected for the different parts of the collection. And so it is needed some method in order to make a prediction which has some guarantee to be accurate. Well, handwriting recognition belongs to a class of tasks which can be called sequential decoding, such as speech recognition, machine translation, etc. In particular, in handwriting recognition, the objects of interest are words. In reality, are regions of images that contain a word, is the object of interest. And the task involves not only object classification, but also word detection, object detection, because you have to detect where there is a word and then to classify this region of image into a class. And the number of classes is huge, generally on the tens of thousands or on the hundreds of hundreds of thousands, because this is the number of different words or lexicon. These are the classes. And many classes are very similar, so it is a difficult classification task. And a final complication is that the empirical error here is not modeled by the classical classification error, but the so-called word error rate, which it also measures the error of detection. That is how insertions and deletions of regions that were not in the ground truth. The technical details of all these are at the end of the view graphs, but let me show you how we should redefine the task of image classification in order to approach what we face in handwritten recognition. A similar task would be to classify each of the animals, each of the objects that are in this image, into one of some tens of thousands of classes, which are the names of the animals. So the result of this classification would be things like tapir, guanaco, spectacle O, there are two, spider monkey, etc., down to king crown butterfly, which is this one. This will be a task which will be rather similar to the task here, where the objects are these small regions which have to be detected, and once detected, they have to be classified, and the result will be things like Rivera, which is right here, concejos, alcaldes de Merced y otras justicias, regidores, caballeros, which are the words here, etc., down to the Portugal, y no haga ni consienta hacer. So this is the task we face. And so, what are the results? We test this in 3 large data sets. One is called the Finnish Course Record, it's written in Swedish. This is Benham Papers, which is written in English. And this is the Norwegian V3 data set, which is written in Norwegian. For instance, in the case of the last one, we have 115 pages for evaluation, which means that we have more than 16,000 objects to classify, which are the words, the running words in the images, in these 150 images. And the vocabulary is close to 100,000 different classes, from which only a few appear in the test set. These are the results that we achieved. This is, again, the empirical word error rate, and this is the predicted error using the methods we propose. Again, they are fairly close enough to be useful in many applications. In this case, there are many applications that are waiting for this technology to be used. These are the calibration curves. Here, the points are the pages of the collection. Each dot is a page which has many words, and so this is the calibration curve, and this is how the same calibration curve behaves on the evaluation data. This is for Finnish Course Record. This is for Benham, almost linear, and this is for Norwegian handwriting. Well, to conclude, we have developed adequate techniques to achieve fairly accurate predictions of error of a system without the need of ground truth data in order to compute this error. These techniques have been applied to many tasks. In all the cases, the results are good. For instance, in all the cases, except for a few cases, the relative error are below 6%. And we hope this kind of accurate error prediction methods will eventually help developing wise and therefore intellectually humble artificial intelligence systems. And thank you very much for your patience and for the 5 minutes that you have allowed me.
Thank you, Enrique. Questions?
Thanks, Enrique. Very nice work. Why did you use the power function? Did you consider alternatives, or it was for you was straightforward that should be the right function?
The ways?
Power.
The power function.
Power function.
Well, it was, well, you know, this kind of trial and error, to try other things, and finally, it is an interesting question because now we are thinking in revisit the theory in order to see whether this makes sense. I mean, whether there is this functional relation is supported by the theory to be a power function. Because in all these cases the tendency was convex.
Yeah.
But we have many other examples in which it is concave, and the prediction is still very well in any case. So it is flexible enough. The only problem we are facing is with systems that are based on very large classification or recognition, like transformers and things like that, where the posterior probabilities that you can get from these systems are, let's say, very bad. They are not really, they cannot be really considered, because typically they are 0, 1. And so it is impossible to calibrate a 0, 1 function with respect to a function that is not. And then in these cases, typically you also find an offset. So the curve does not go through the origin, but start. But in any case, in these cases, the results are very bad. So this is one conclusion that I didn't have time to mention, but a conclusion is that as more ambitious are the modern systems, the more far away from the theory they are, and also the posterior probabilities that they provide become worse and worse and worse. And so.
More questions?
Well.
Okay.
My quick question is, so how different is this is working, yes, from just using the resubstitution error, just asking what your accuracy is on the training data?
I didn't understand. My error is a bit much.
So you're calculating an error rate based on P of X and then P of C given X, right? Mm-hmm. But you could use just the training data itself and ask how accurately you're fitting the training data. And I think, Leo Breiman would call that the resubstitution error, right? Because you're treating your training data as if it were test data. Does it make a difference?
Ramon, can you help you? Can you help me? I'm sorry.
Instead of P of X and the conditional probability P of C of X, using what?
Just using the training data.
I mean, the training data.
You're right. Instead of calibrating its probability.
Instead of calibrating the probability using the training data.
Yeah.
I mean, they both use the training data, but this method calibrates.
Yeah. For calibration, you can use the training data. And also another approach that can be carried out that I didn't mention is to calibrate the posteriors in the first place. There is a lot of literature on posterior calibration. And we have tried that, and the results are inferior. So typically you get better results when you go directly to calibrate the thing you want to calibrate rather than a primary value. I don't know if this is what you asked or more or less.
Yes, thank you.
Okay, thank you, Enrique.